In this video, we will discuss the trigonometric functions sine and cosine through examples related to sound. When we hear a sound traveling through air, the sound is the change in air pressure caused by a vibrating medium, like a vocal cord, guitar string, saxophone reed, etc. The air pressure is changing to be above and below the stable air pressure. So in this sense, we have oscillating air pressure. When we consider how frequent the oscillations occur and the maximum pressure attained above stable air pressure, it makes sense to consider the sine wave as a model for sound. Furthermore, the mathematician Joseph Fourier showed that all complex waveforms can be decomposed into sine waves. So we will start by focusing on the sine wave. When you learn how to graph the equation y equals sine theta, you get the following graph. You also learn about amplitude, period, and through some examples you learn about frequency. To see how these terms show up in the example of sound waves, we will use time as the horizontal axis and pressure as the vertical axis for our sine graph. In this example, amplitude is the highest air pressure reached above equilibrium, which is stable air pressure. This also relates to our ears as volume. Period is the amount of time for one cycle of oscillation to occur. And frequency is the number of oscillation cycles that occur in 1 unit of time. This also relates to the pitch of a note to our ears. Let's consider middle C on a piano. If we put this sound into an oscilloscope, we can see that it is not a simple sine wave. As a comparison, here is the graph and sound for a pure sine wave at the same pitch as what was just played on the piano. So while these two sounds play the same pitch, they are both very different. This is because the strings on a piano create a complex sound. However, there is a fundamental tone that is the most dominant. We can see this by playing this sound into a spectrum analyzer to see all of the frequency information. What we are seeing in the spectrum analyzer are all of the frequencies that make up the complex piano sound. These frequencies are measured in hertz, which is abbreviated Hz and stands for 1 cycle per second. The fundamental frequency for middle C is 262 cycles per second, or 262 hertz, which also means that the period is 1 cycle for every 1 over 262 seconds, or 1 cycle for every 0.00382 seconds, which is the same thing as approximately 3.82 milliseconds. Here is the graph and sound for a pure sine wave set to 262 hertz. When we hear this, the air pressure is oscillating up and down 262 times per second. The amplitude for this wave is set by how loudly it is being produced. The louder the volume, the greater the change in air pressure from stable, the higher the amplitude. Notice the change in volume and also the height of the amplitude when I raise the volume up and down. This is why we use the word amplifier for our stereos, as they control the range of volume in the sounds we hear through them. There is another term that is not mentioned in a trigonometry class, but is a fun concept to consider: wavelength. This is similar to period, but instead of measuring the cycle in time length, we use measurements of distance. Wavelength is simply the speed of sound divided by frequency. The speed of sound is approximately 1,130 feet per second. So for our 262 cycles per second sine wave, the wavelength would be 1,130 divided by 262 feet per cycle, which is 4.313 feet per cycle. Finally, how does all of this relate to cosine? There is an easy identity to start with. Since sine and cosine are cofunctions, cosine theta is equal to sine of 90 degrees minus theta. What this means in application is that a cosine wave is created through a manipulation of a sine wave. We can see what that manipulation is by using another identity. Starting where we left off, cosine theta is equal to sine of 90 degrees minus theta. This is equal to sine of negative theta plus 90 degrees, which, because sine is an odd function, becomes negative sine of theta minus 90 degrees. This result tells us the following. If we take our original sine wave, shift it horizontally by 90 degrees, and then flip it vertically over the horizontal axis, then we will get a cosine wave. We can do this specifically with our 262 Hz sine wave from before. Since 262 Hz is equal to 262 cycles per second, this is the same thing as one cycle for every 3.82 milliseconds. To shift this by 90 degrees, the waveform would need to be played 1/4 of a cycle later, which could be done by delaying it by 3.82 divided by 4, or 0.955 milliseconds. And then the waveform would need to be inverted or flipped vertically. I can achieve both of these things with a little piece of recording gear called a phase alignment tool. The shapes look the same, and when played separately, they sound the same. But when the cosine wave is blended with the sine wave by mixing, some slight change to the sound occurs. Let's listen to notice the difference. First, here's the 262 Hz sine wave by itself. Next, here's that same sine wave, but mixed with it is the cosine wave played at the same time. Notice the slight change to the sound. Finally, to be more extreme, here's the original 262 Hz sine wave again, and this time played together with another sine wave that has been shifted horizontally 180 degrees. The two waveforms are severely out of phase, which means when they are added together by mixing, a lot of the sound is canceled out. These things are important to recording engineers when using many mics to record an orchestra, drum set, or even a piano. When sound waves are out of phase with each other, it can affect the overall recorded sound. So recording engineers use mathematics, precise measurements, and devices like this one to keep the sound waves in phase. While sometimes we would like to have sound waves be in phase, there are other times where it's pretty interesting when waves are out of phase. This became such an interesting effect, a phaser was created. Here's an example of what that sounds like on guitar.